A developer opens a command line interface and types a standard directive: make the failing test pass. The common assumption is that a single, highly intelligent frontier model receives this text, solves the engineering problem, and outputs the result. The raw language model is entirely stateless. It is a swappable inference engine designed only to predict the next token in a sequence. The actual capability comes from the agent harness. This is the complex software architecture that wraps around the isolated model call. We are going to trace a single command directly through the OpenCode Go harness to see exactly how production agents are engineered. The entire system rests on two structural pillars: a single SQLite database connection and an unbounded execution loop. True agentic behavior, persistent memory, physical file system access, and operational safety is engineered into the surrounding architecture. It is not prompted into the model. The prompt enters a function called run. It hits a strict concurrency guard. The system enforces one active generation per session, rejecting secondary requests. The system stores a session-keyed cancel handle, guaranteeing the user interface maintains authority to interrupt. With the guard in place, the harness spawns a background Go routine to handle the text generation asynchronously. The thread drops into an unbounded React loop, where the simulation of intelligence happens. It executes until hitting a boundary called stream response. Here, the harness pauses internal logic to call out to the third-party LLM provider. By wrapping the unpredictable text generator inside a strict for loop, the harness forces the model to iterate within defined software rules. All state for this loop lives in a single SQLite connection, divided into three core tables: sessions, messages, and files. Waiting for a language model to finish a long generation before saving state exposes the system to data loss if the process dies. To prevent this, the harness creates an empty assistant message row in the database before the model generates a single word. As text and tool use deltas return from the API stream, they are injected directly into that empty database row, character by character. If the connection drops or the user hits cancel mid-generation, the system retains a perfectly durable partial transcript on disk. The LLM finishes its streaming output with a formal request to execute a system command, rather than returning plain text. The harness intercepts the request and matches the proposed command against a strict registry of exactly 11 built-in tools. When the model invokes the bash tool, it drops into a persistent shell environment that enforces a hard 10-minute execution timeout. Long shell outputs threaten to overflow the LLM's context window. If a command returns more than 30,000 characters, the harness aggressively slices out the middle of the response and replaces it with a summary line count. Every time the edit or write tools execute, the harness writes an absolute snapshot of the new content into the database, tagging it as version 1, version 2, and so on. This database snapshotting provides the actual rollback mechanism. It anchors the workspace in factual file states, bypassing the model's tendency to hallucinate previous code structures. Handing an unbounded code loop direct access to bash and the file system creates an immediate risk of catastrophic data loss. The architecture implements a permission gate. This is a blocking channel inserted immediately in front of any mutation or network command. Commands from an explicit read-only allow list, like git status or ls, bypass the gate entirely. Write operations, edits, and general shell commands hit the wall. The execution thread halts indefinitely, waiting for a human operator to physically grant permission through the user interface. As the session iterates through these loops, the historical transcript accumulates until it threatens to exceed the LLM's context window limits. OpenCode does not contain an automatic memory compaction system. The human operator must manually trigger the summarize function. Calling summarize routes the entire session transcript to a separate, cheaper LLM, configured solely to compress the text into a dense summary. The harness saves this compressed text, generating a summary message ID database marker. On the next iteration, the system slices the history. It only feeds the model messages occurring after this anchor. Older messages are ignored, but remain preserved in SQLite. The system presents an illusion of autonomy, but core safety checks and long-term memory management depend entirely on human intervention. The OpenCode system prompt explicitly instructs the LLM that it is operating within a secure, sandboxed workspace. The engineering reality is different. The OpenCode repository lacks any operating system-level isolation primitives, virtual machines, or secure containers. execution security relies exclusively on a hard-coded list of banned bash commands, working directory confinement, and the requirement for a human to click Allow. When stripped to its base components, the agent is an unbounded React loop, an incremental SQLite database, and a series of manual memory anchors. Reliable agent deployment requires rigorous systems architecture, a robust framework designed to wrap and contain unpredictable software outputs.